So we can probably work on this little screen here. So you can use, if you've got any questions, just ask on that side. Can I make this any bigger? So we'll run through, oh, that'll be fine. So let's begin with the idea of a moment function and what it means. A moment function is just a fancy way of recapitulating or reformulating the restrictions that we're assuming. So assume we've got some data set, y1 to yn. So these are observed data sets, and that was drawn from some distribution y1 to yn. So we often use capital Y to denote the random variable and little y1 to denote a particular draw from that distribution. So you could think of the y's as, say, the distribution of GDP in different time periods, and this is the particular, and then we've got the little y1 is our outcome. So you can think that this is just some joint, it's just a vector random variable that's going to have some joint distribution. Call it f of y. Now everything you've seen up to now, we've assumed that all the data samples come from an identical distribution and they're all independent. So this IID assumption. You don't need to assume this. We can actually just have a general joint distribution, call it f of y, and that's unknown to us. It's just some, it doesn't need to be really known to us. It's just some, what we're saying is that our data set comes from some joint distribution, some data generating process that has got some distribution. We'll just kind of work under the assumption it's IID. It's not really going to change all that much. It's just all the key ideas come whether it's IID or not. Well, let's just take then the simplest example of restriction. Well, let's say we want to estimate, or we want to look at the model or for the mean. Well, we have E of yi, again assuming it's IID, so the mean of this equals, call it mu naught. And we don't always talk formally, but this E is taking expectations with respect to this true underlying density f of y. Now we don't always write that because it gets cumbersome after a while, but we often skip all the details. But this formally is the average of yi taken with respect to the underlying population distribution of our data set, where it came from. So it's whatever this joint distribution is, we take the average with respect to that distribution. So for example, it could say be a normal distribution or whatever distribution, but that's unknown to us. The point is, we want to take we want to see what's the mean of this distribution, y. We'll call it mu naught. Well, we can rewrite this again. We'll drop the f of yi just to keep the notation simple. But again, always bear in mind what this E is. It's the average of this variable yi with respect to the underlying population distribution or data generating process. That's unknown to us. So the whole point really is to make some inference on the properties of this distribution that generates our data set. One thing is we want to go around looking at formalizing how we could go around estimating the mean. Well, we first start with the population problem. This is our unknown parameter. We want to estimate. We want to go around estimating, and we're just setting up now the general population problem. We can rewrite this as E of yi minus mu naught equals naught. All you're doing is taking this to the left. I mean, there's not really, you wouldn't really, this is just, you don't normally do this in practice, but you technically can take it to left hand side and we can think of mu naught satisfying this. Or another way we can write that is, we can take the set, call it M, of all mu belonging to the real line. This is just really formalizing this now, where this moment condition holds. E of yi minus mu equals naught. So this really fancy technical way of saying let M be the set, we use a curly parentheses here to note the set of all constant scalars mu on the real line anywhere between plus or minus infinity, where this function of mu equals naught. Well, we can see from above there's only one solution, and that's that mu equals mu naught. So it's just a really roundabout way of saying that mu naught here is the value of mu that will set this equal to naught, and by definition it's the population mean, which we call mu naught, namely E of yi. So we can see in this case M, the set of all solutions to this moment condition, is just the singleton mu naught. Now you wouldn't do all that for the mean. That's going over the top. You wouldn't obviously do that. There's not really much need to do that. It's just to unify the theory that technically, really, everything you've seen can be expressed as the solution to some restriction or some moment condition from the true density of y. So we can see here then, we can just call, so we can generalize, we can call this is just a function of mu and yi. So we call that g. Let g of yi and mu just be yi minus mu. Well, another way of saying that then, with a mu naught is just the value that sets this E of g yi mu equal to naught, and it's got one unique solution. Again, it's a shorthand for this. There's only one value of mu that satisfies that, and it's the population mean mu naught. Right? Well, the method, so that defines then what this, that's all parameters that's consistent with that restriction, this moment restriction, this moment condition, E of this function equals naught. Now, of course, the properties, of course, are going to depend upon, in general, the true distribution with respect to what you take this expectation with. In this case, we can see it doesn't matter what the distribution of y is, so long as the mean exists, which is a very minor condition, then there's only one unique solution to this moment condition, and it's the population mean mu naught. So then, the method of moments is a form of estimation which then estimates this mu naught, and all it does is it uses the fact that this mu naught, the solution at the population level to this moment condition is the parameter of interest mu naught. Well, we can solve the sample version by just enforcing the sample version of this population moment condition. Namely, we can choose sigma g yi mu equals naught. And note the distinction. The capital yi is the random variable. Capital Y is a random variable that takes different values of y with different probabilities, and this takes the average over that. This here is the sample average of this function evaluated our sample data from which was drawn from this population distribution. So the capital Y is a random variable which takes different values with different probabilities. We've enforced the sample version. We take the sample average of this moment condition and we solve for this. And this is the definition in this case of the method of moments estimator. Okay, and in this instance, this is exactly solvable because we've got one moment condition. This is a 1-by-1 condition, and we've got one parameter. So it's exactly identified. This here is an exactly identified system. We've got one parameter, mu, to solve for, and one moment condition to do it with. Well, all the method of moments does is it takes the population problem and it solves the sample equivalent. And what you can see then, all you got to do is plug in the moment function, and you can see the solution to this is just going to be, without much surprise, the sample mean. So if we plug this in, well, plug in the g function, we want to find the value of mu, which makes this equal to naught. Well, just expand out the left hand side, we're going to get 1 over n sigma yi equals 1 to n minus the average of mu, which is mu because it's constant, equals naught. Well, the solution, call it mu hat, is just the sample mean. So this is kind of a long-winded way, but what we're showing here is that even the simplest, really one of the simplest examples of an estimator well, you see, well, let's just do it here. So we have then, so this just implies, well, simply to solve mu hat, the method of moments is sigma yi 1 to n by I. sometimes we call this just y bar for short, the sample average of y. Right? So we've seen that the mean, sample mean, is just a method of moments estimator for the unknown population mean. The population mean solves this simple population moment restriction, and the sample mean solves the sample version. And then we can start to look at the properties of this sample average. Well, assuming the data's IID, in this case, by the law of large numbers, this mu hat will converge in probability to mu naught. Namely, the solution to the sample moment condition, the parameter mu that solves that, will eventually converge and get nearer and nearer and nearer in probability to the solution to the population problem. Okay, and broadly speaking, that's because the sample average converges to the population average. And so the solution then, assuming it's all continuous, which it is here, it's a very simple linear function, then the solution to the sample condition should converge then in probability to the population solution, and it does under some assumptions here. And that really is that one of the whole underarching ideas behind a big deal of econometrics that you're going to see is we can always think of we're going to have some restriction. We may just assume one, it may come from some economic theory, which we can often write as a set of moment conditions where we believe that the true parameter solves this. We can then see what parameters are identified, namely how many parameters are consistent with that restriction, and we can then go about coming up with trying to estimate this parameter. So the whole notion of identification is looking at, really, we have some restriction that we're assuming, and we want to see how many parameters are consistent with that restriction under the true data generating process. For the sample mean, it was straightforward because there is only one solution, and that doesn't depend on the distribution of y, one population mean, and therefore there's only one solution. Let's take another example we've seen then. So suppose again now we've got a linear model where yi is equal to xi dash b, say naught, plus ei, and we assume that this b naught satisfies this, that at the true parameter ei xi equals naught. So this here is a model which is a linear model assuming the exogenate condition. So identification broadly is not really concerned with whether or not these assumptions actually hold at the true model, but is what models are consistent with these two restrictions. Namely, we can rewrite this as a moment function where we can rewrite this where beta is a solution to the residual at any beta. So we're choosing b naught, some fixed parameter, beta we're choosing. We can see how many models or beta solve this. We can see here under these two assumptions, well, b naught would satisfy this. We can also see if any other values might satisfy this as well. And there'll be some conditions when there could be more than one solution. So this here is a model which comes from this. We've got the linearity, and we're enforcing this restriction, this moment restriction, and we can rewrite this in this form, and we can see, we can define as the set B all, we can think then, I should have written it, let all B belonging to, I'll rewrite this again. Well, let's just another. So then we can again write this as a moment condition. All that means is we can just write this generally as this is just an example of a moment function. So this here we can call g yi xi, so it's a function of y and x now, and b. You don't need to do that, but you can see we can just call it some function of beta and y and x. And so we can just call it generally this. We can we can see then that in this case, call B, let B be the set of all betas belonging to the r to the p. So on the pth ordered real line, So each element in essence belongs somewhere on the real line. So it's a p by 1 vector, and each element lies somewhere on the real line, which basically just means anywhere. And then we want to find all the betas that are consistent with this restriction here. Again, you can write it. We can write it in the G form, but in our case, we want to look at how many betas solve this, because there may be more than one, depending upon what the true distribution of y and x is. And remember, this E is taking expectation with respect to the joint distribution of y and x, whatever that is. So it could be anything. Okay. Well, we can then just solve. So this is just saying define B as the set of all vectors beta which solve this moment function condition here. So that's, again, it's kind of a fancy way of just saying that in words. That's what it's saying. B is defined as the set of all vectors that satisfy this condition here. So then we can then just solve it. So expand this out, and we get E of yi. Again, yi is a scalar, xi is a p by 1 vector, minus E. Now we're going to have vector multiplication. So this is 1 by p, this is p by 1, this is p by 1. So we left multiply. It's all going to be, this is going to go here. So we're going to get, they've all got to be consistent. So we left multiply when we multiply by a vector. Xi dash beta, okay, equals not. Beta comes out because it's a constant. So this is now a system of equations in beta. This here is just some p by 1 vector of numbers, and this here again is a p by p vector of numbers. Okay, so it's going to have all the second moments of xi and squared and all the cross products. So we can see, well, when is this solvable? Well, that's it. That defines all these beta. We can rewrite this again as this is equivalent. So this is just equivalent. All this is equivalent to the solution here. So this is just a linear algebra problem. You can call this C, call this A, and call this X. We've got a system AX equals C, and we want to solve for X, which is our beta. So we can see there's a unique solution when here, again, it's exactly identified, because this here is a p by, this is 1 by 1, this is p by 1. This is a p by 1 vector of a equation. So we've got p by 1 moment functions here, and p parameters. So it's exactly identified. So we can see then there's a unique solution when A has full rank. So x is a to the minus 1 of c. If A is invertible, it's full rank. So we need this here to be full rank, which this being full rank just means there's not any linearly redundant combinations of x. So for example, which we call multicollinearity, there's no multicollinearity. For example, including the same variable twice, then it wouldn't be full rank. But even if they're, so we can see in this instance, the solution set B does actually depend on the true distribution of y and x. In order for there to be a unique solution, there has to be the distribution of y and x has to satisfy that this EXX transpose has full rank. So for all distributions y and x where that is full rank, there's a unique solution. Otherwise, there'll be an infinite number of solutions governed by the solution. Oh, the pen's gone. What? Governed by this. One sec. Right. Okay. So if E of X transpose is full rank, well, it's just again, it's a for any distribution y and x, again, assuming that these moments exist, which is, for now is a relatively minor condition. This here, for every different distribution of y and x, this can be a different vector of numbers, and this could be a different matrix of numbers. And so you can see the solution to this in general will depend upon the distribution of y and x, because these are just moments from the distribution of y and x, which can differ depending what the distribution is. And that's what I was saying about the identification. The number of solutions can depend upon the distribution of the data that generated data we observe. In this instance, we can actually verify whether or not that's full rank because we can tell if we've included some linearly redundant combinations of regressors. In fact, data will just tell you when you put it in, or R will tell you if that's the case. Okay, so that's it. We can do another. So it was exactly identified, and we've got the system of solutions B. So we can do another example of instruments. So let's now again assume a linear model yi plus ei. Xi is a p by 1 vector, and so the xi is p by 1 vector of regressors, and assume we've got some m by 1 vector of exogenous variables as instrument called z, and we then this just means we've got this where zi is m by 1. So we've got our m vector of exogenous instruments and p vector of regressors, which could include exogenous or endogenous variables. Then we've got now two restrictions, and we can then set up the model. So we can then find, again in this case, our moment function is going to be, well now it's called going to be a function of y, x and z. Well, it's y minus xi dash beta. Again, b naught some fixed true parameter, and beta's the thing we're solving for. Why does it always do this? Times zi. So in there, all we're doing is replicating this and solving for all betas which are consistent with these two restrictions. This is our restricted model that we're going to look at and see whether there's how many solutions there are to this. Well, we can see in our case then, assuming these are true, b naught will satisfy the expectation of this. Namely, we can look at the set of all values b, where this means b is defined as, again, all the betas belong to the p real line, where the average of this moment function, which we call, again, you can generally call it g, but this is our moment function. So again, this here just says the solution set, so the number of betas that are consistent with these restrictions, which we're assuming that hold on the true distribution of y, x and z. Well, b naught will satisfy this. We can see then, because if these assumptions are true, at b naught this would just equal ei, and then we're assuming at that this restriction holds. So b naught will solve this under these restrictions. We can also find how many other values will be consistent with this. Just to be clear, when we look at this from an identification viewpoint, we don't actually need these assumptions to be true at the true parameter. We can, even if it's not true at the true parameter, we can still look at what will be the values of beta consistent with this and see when it would and wouldn't have a unique solution. So identification, broadly speaking, is not concerned with causality or whether it's a true model. It's just if we believe our models, if we want to look at how many parameters our models are consistent with this restriction, and that's all it looks at. Whether it's a true model or a biased model is irrelevant. Is there one solution or more, and what does the solution set look like? And this will become important because the properties of our estimator, one of the key assumptions we need to use a standard estimation methods like method of moments and GMM, maximum likelihood. To use all the standard theory, we need to have that this moment condition has a unique solution. If our model doesn't have a unique solution, a lot of these estimators have non-standard properties. So that's why we do it. But to begin, it's just an exercise to say when will this have a unique solution and when will it not. Okay, well we can then do the exact same thing. We can rewrite this, expand it out. We're going to get e yi, again, a scalar, times by an m by 1 vector. So this is m by 1. Minus, again, left multiply, you're going to get e of zi, which is m by 1, times xi dash, which is 1 by p. That's m by p times a p by 1 vector of coefficient equals naught. And again, this naught is then an m by 1 vector of naught. You've got a system of equations. So here, and that's it. So b, this is again to be solved for b. We want to find the b that's consistent with this restriction. And that's our, so the this would then be our instrument model. If we want, so we can then see, so we can see straight away some results. If m is less than p, then it's not identified, it's under identified. So there's not as many moments as instruments or moments. There's not as many moments as parameters. So we can't. There can't be a unique solution here. If m is less than p, we can't solve this because there's p parameters. Let's say there's 5 parameters and 1 moment. You've got one equation to solve for 5 parameters. So of course you can't do it. M equals p would be exactly identified. Which may or may not have a unique solution. It would depend on then the rank of this. When m equals p, this is a square matrix. And this may or may not be full rank. It depends on, kind of, broadly speaking, it's going to be related to the covariance between all the z's and the x's. So there's no reason why this is full rank. In fact, this could be not. Let's say that the z's and the x's are all uncorrelated, and this, in some instances, this can be not. Okay, so this may or may not be full rank. It depends on if there's sufficient variation of the x's and the z's together such that this becomes full rank. And then m bigger than p, it's over identified, and again, well, in this instance, there'll be there'll be no solution here, right? Because, well, it'll not be uniquely solvable here, because if m is bigger than p, you can't solve, if you've got 10 equations and one unknown, then you can't solve all of them. But again, it will still be just one beta that will satisfy this, but you won't be able to solve this uniquely. You'd have to use, so we'll come back to this, but let's just start with the exactly identified case, when you've got as many instruments as you have regressors. Well, in that case then, so at the broadest level, this is it. Beta is all the values that satisfy this. If m's less than p, there has to be an infinite number of solutions, because there can't be, we've got more equations than we've got unknowns. More unknowns than we've got equations, sorry. More parameters to estimate than we've got equations to solve for. If m equals p, it may or may not have a unique solution. It depends on this matrix having full rank. So we can see then, but what's the condition? Let's just take the case where we've got exactly identified. Let's take the case where m equals p. Well, in that case, if exi zi dash, which in this case is going to be square because it's m by p and we're assuming they're equal, so it's just going to be m by m or p by p. If this is full rank, column rank, then we can solve. Well, it's going to be square in it, so if this is full rank, we can solve. So then we can solve this system of equations here for beta. If this is invertible, you can multiply both sides by the inverse, and you'll find in that instance, when it's exactly identified and that's full rank, then beta, the one solution to this is going to be e of to the power minus 1. Otherwise, there'll be an infinite number of solutions. If this isn't full rank, then you can have an infinite number of solutions, Let's give an example then, where let's just say we have one instrument and one regressor x. Well, in that case, we can see. Well, sorry. Let's do a two moment one. Let's do an over identified example and see. Let's give an example then. So we saw what we just did then was we saw under what let's take the just identified or exactly identified case. We saw there's a unique solution for all distributions of x and z and y where this is full rank. For some distributions it will be full rank, in other ones it won't be. If it's not full rank, then there's going to be more than one solution to this system of IV moment conditions, which we don't want to happen because then it won't be identified. And the IV estimator will have non-standard properties if there's multiple solutions to the population problem. And it makes sense if there's multiple solutions to the population restriction. When you solve the sample version doing method of moments, well, it's not going to be solved at any one particular. It's not going to be solved at near to the unique solution at the population level. It can dive all over the place because there's multiple solutions. So you're going to get a flat spot in the optimization function when you do the sample version, and you're going to, what you'll find is that the actual sample method of moments estimator will itself converge to a random variable. It will not converge to this fixed solution. Let's give an example. Let's do an over-identified example. M equals 2 and P equals 1. So in that case you've got two instruments, Z1i call it, and Z2i, and you've got just one scalar regressor. So in that case, well, we've got our general solution system. We've got E of the, again, we've got, this is it, we've got yi, which is again a scalar, times by Z1i, Z2i. That's a 2 by 1 vector. Minus, now we've got E of, so Zi is a scalar, sorry, 2 by 1 vector, times by EI, which is a scalar, so it's going to come inside here. Sorry, XI. XI is a scalar now, so we can multiply both elements in the vector by XI times beta, which is, we've got one regressor, remember, so there's just a constant, be 1 beta, equals naught. This is 2 by 1, this is 2 by 1, and this is the one scalar coefficient on x, which you want to solve for. Okay, so we can see here that we need, for this to be solvable, we need that this has got to be full rank, which just means at least one of these expectations can't be not. So this really just gives us two equations. We've got E of yi Z1i minus B E of Z. That's the first equation. So we can see if this doesn't equal naught, we can solve, and there's one unique solution for beta. If it's not, then this is then not a function of beta, so any beta will solve this. If this is not, this will be not, and any beta will solve this. Because if this is not, if you change beta, it doesn't change this, so there'll be an infinite number of solutions. So you can't, or another fact, another way is you can't, it's not solvable for beta. And the second line will give us EYI, a second equation for equals naught. If at least one of these doesn't equal naught, then we can solve for beta. If both of them hold, we've got two equations for beta. Now we can't, of course, we can only take in the end one estimate for beta. If they both hold, we've got two restrictions. If they both are not, both of these elements in the green box are not, we've got that beta solves two restrictions. Now that gives us two restrictions to identify one parameter, which gives us more information, or what's often called over-identifying information. But we can see for beta, for there to be a unique solution here, there has to be at least one of these elements not equal to naught, which just means that this vector is full rank. At least one. If one of the elements is not naught, then it's got rank 1 and it's a full rank then. It's full column rank. Okay? So, and this is where the rank condition comes. It's got to have full rank in order for us to be able to get a unique solution for B. And again, you can generalize this up. So let's just say the first condition holds this, and there's one unique solution. That just means B equals E of yi Z1I divided by E of, which would then just be the simple IV model then, xi. Sorry, yeah. We can see in order for it to be solvable, this has to not be equal to naught, otherwise we can't do it. Okay, if this one held as well, we can also write beta as similar this way. So we could use either of these as estimates. And really, all the GMM estimator does, which you're going to talk about more later in the lectures, is when you've got more in moment conditions, then you have divided by Z2I xi. To solve if that, again, assuming that this doesn't equal naught. Now, you've got beta satisfies two restrictions, they're equal to each other. You use one or the other. Using one or the other would just be IV, but what you can do is you can construct a weighted average of these two where the weights sum to 1, and that will also equal beta. And really what GMM does is just when you've got multiple when you've got more moments than parameters, it takes a weighted average of these estimates and it'll choose the weight to make the estimate as efficient as possible. So we won't dwell on that now, but that's why when you've got more moments than you've got parameters, so long as the rank condition holds, there'll be one unique solution, but now you've got multiple equations with which to pin down beta. So you can choose an optimal weighted average of them to get the most efficient estimate that you can. But broadly, again, going back to the overall idea, this is all sets of B that solve this moment restriction above. And we can see very clearly now that the solution set, how many B to solve this, depend upon the underlying distribution of x and z and y. When this is full rank, it's got a unique solution. Otherwise, there'll be an infinite number of solutions which solve this, and that will define the betas that are consistent with this restriction. Okay, so that's the idea of identification. There's some we'll leave that for question 1 because we went through, but there's some other bits, but it's all the same idea. The next bit then is applying it to a new example. So you've already been working really with moment conditions when you've been looking at IV, OLS, and working at these are all examples of restrictions that can be formalized as a moment condition, the solution to some moment condition, and maximum likelihood as well. So all three of those can be expressed as the parameters can be expressed as a solution to some moment condition. Well, this all generalizes another example. So sometimes moment restrictions are implied by economic theories, and question 2 was looking at the Euler, the intertemporal consumption maximization problem, namely the first order condition. Under all those macro assumptions, the first order condition says that the marginal utility of consumption at time t is equal to the average marginal utility next period I think this was it, right? Given this. Was it divided? I forget. Wait, someone, was it divided by? I forget this. I think it's divided by, right? No, it's times by. Anyway, I think that's it. I think this is it. Where gamma. Correct me if that's wrong. Omega t is what's called the information set at time t. All it is all variables that are known to the consumer at time t. So it could include things like it will include, for instance, their last period consumption. So CT will belong to the information set at time t. It could also include things like previous interest rates or any other economic information from the past that they've got. So you'll have seen this before from macro. This then is what the distribution for consumption and interest rates should satisfy. So think again now, there's some distribution that's generating consumption and interest rates and all the macro variables, but this one's focusing on the consumption and interest rate across time, and under this macro model, this where we believe then that this restriction holds. So the first bit was to ask that you can rewrite this like that way you can take u dash ct to the other side. So you can take u dash ct to the other side. So sorry, this, yeah, expectation, this given this at time t, which is for shorthand written et. But this is what it is. We've got e, b, u dash ct plus 1 given the information set at time t. So you can take that marginal utility at time t. This is for part 1 equals not. Well, ct belongs to the information set at time t. So when you can remember, conditioning on the information set means conditioning on all the information you own at time t to the agent, which includes their consumption last period. Therefore, it's just fixed. Once you condition, it's then fixed. You're saying we know what that is from last period. Again, so we have then, we can take that inside. This is just an equivalent to e of beta u dash. So again, beta is the time rate of preference. I forget the names of these things, but I don't do macro anymore. Given minus u, the discount factor, minus u dash ct, given this. So again, and this is because it's known at ct is part of the information set at time t. Another thing to add is this holds for all past information set. That's the key thing. This holds for whatever values happened in the past for consumption interest rate. So this is a restriction which says the average of this nonlinear function here, some random variable, given the past outcomes of the consumption interest rates and so on that were known to the agent, is not whatever happened in the past. So for all possible past outcomes in the information set. So for all possible past consumption and interest rate streams, that's what that says. Okay. So the next bit then says, so this then is a conditional moment restriction. It's a little bit like a nonlinear version of the zero conditional mean assumption, where you assume that at the true parameter, the expected values of the unobservable in the linear model, given any possible value of x, so the regressors, is not. So this is kind of analogous to a zero conditional mean restriction, but of course it's not a conditional mean. It's not in this particular instance. It's not. This of course is not just a standard residual from a linear model. But it doesn't matter. We've got, well, this variable should satisfy the restriction, namely this. If the restriction is true, at these parameters, this beta and whatever this utility function is, the utility function and the beta should be the true utility function and beta should be that this random variable is mean independent of any possible outcome in the past. That's what this says. So broadly speaking, it's saying it's uncorrelated with any kind of function. This unobservable, this random variable at the true beta and utility function should be uncorrelated with any function of outcomes in the past. Again, so that may or may not hold, but we can now, so that was part 1. Part 2 was then to show that if we've got some subset information, say zt, that belongs to the whole information set. So this, for example, could just be say past consumption and interest rates. Well, of course, that's going to belong to every possible known variable at time t, because this could include, of course, rt minus 1, ct minus 1, ct minus 2, and back forever. So you get this is a bigger set than this. So this is just saying that we've got some kind of vector of information at time t that the econometrician observes, that is part of the information set that the consumer observed. So remember that in practice, the econometrician can't observe everything the consumer observed. So this omega t, this information set, is everything that was known at the consumer at time t. and we're saying we've got some variables zt, some of them. So it may, common examples that are used in applications are like so many legs of the consumption and interest rates are used, but of course we can't really include all of them. Okay, so that's the intuition behind it. The next bit then was to show that this implies that the expected value of this u dash ct plus 1 times 1 plus rt given zt equals naught for any value of zt. Well, intuitively you can see it will, right? The above condition says here this, that the average of this nonlinear, this function, this bit, the average of this given for any possible value for all variables information set has got average naught. So of course intuitive it's going to apply that the average of this given some subset of that takes some particular values also naught. And you can also see this by the law of iterate expectations to show it formally, namely really what we've got here, to write it in a general framework, just call all of this here, just call it xt, doesn't really matter, just call it just for shorthand. So we can write this more for what we're really showing is a mathematical result where the expectation of xt given some information set, sorry, xt plus 1, because of course this is at time t plus 1, this is at time t plus 1, this is last period, so this is saying the average of some variable next period from now, xt plus 1, given the information set at time t equals naught for all possible outcomes in the past, implies that e of this xt next period given zt equals naught for all zt, when zt belongs to this bigger information set. It's a subset of it. That's what it's asking us to show. So this is the result, and it follows just by the central limit, by the law of iterated expectations. This holds, so we can here, this holds for all values of the information set in the past, which includes zt and everything else. So if we take again conditional expectations on both sides, we can take conditional expectations on both sides of this and get e of e xt plus 1 given omega t. So we can take expectations of this over given zt, well, what we're doing here is taking the average of this with respect to omega t given a particular value of zt. So in this particular instance, well, this here is just going to be here, we can now integrate out all the other values in omega t, so this will just equal to so another way to give you could also see it this way. So let's just say we have e of, let omega t equal say zt and wt, so it just includes two variables. Well, in that case then we've got e of some function, some variable next period given omega t, in this case is zt and wt, equals naught for all z and w, implies e of xt plus 1. Just to give a simpler example, just one of them equals naught for all zt. Again, because of course zt belongs to this bigger set. So just assume this information set just includes two variables. Of course, in the real example, there'll be kind of many, but in this, just assume there's just two variables information set, and we want to condition on just one of them. This here says that the average value of xt given any z and all w's is not. So of course, if you then average this across all values of w for the given zt, well, that also equals naught. Well, the average of that is just this, by the law of iterator expectations. So if the average of xt plus 1 for any z and w is naught, well, of course, it's the average value of xt plus 1 given z also equals naught. Doesn't matter what w is, because for every value w, the average was naught. So when you average this across w given zt plus 1, well, by the law of iterator expectations, it's equal to this, and then that's also equal to naught. So that's the idea. And so again, this is really a stronger. This here is saying that the average value of xt plus 1 is naught for any z and any w in the past. So of course, the average value of xt plus 1 given z is naught. It doesn't matter what w is, because for any z, no matter what w is, the average is naught. So you can just take the average. What you can do is take the average of wt here with respect to zt plus 1 of this. Given zt. Well, all we're doing now is averaging across the w's. So by definition, this is just going to be then e of given zt. Again, we're taking the average across all the taking the average across the w's given zt is this. Okay. So that's just a law of iterator expectations, given a particular example. We gave the intuition as well. So again, if the average value of xt plus 1 for all z and w is naught, the average of xt plus 1 for just any given z is also naught. It doesn't matter what w is. So when we average across the w's, we're going to get back to this by the law of iterator expectations, and then that's also naught, because again, we're taking conditional expectations on both sides of this. So all we've done is taken the conditional expectation of this on both sides from w given a particular z. We just average this here in general is a function of z and w, so we're going to average across the w's for a given z. Do this. Well, this also equals naught because we've taken conditional expectations on both sides, and then we've got the result here. Okay, so the next bit then, so then what we've got is, now, from our more general condition, we've got e of beta u dash ct plus 1 plus rt minus rt plus 1 minus u dash ct, given this subset information set is naught for all zt. I think I missed out another bit was, so then so this is general, so then assume then that u dash c is this constant relative risk aversion utility function. So we're now, in practice then, we're going to have to make some assumptions on the form of this utility function in order so that we can then parameterize this and work it out. This is one approach. The simplest example is to assume that utility's got this constant relative risk aversion, so the utility of consumption. The first derivative then is just equal to my c minus gamma. Multiply both sides. When you differentiate respect to c, multiply by this, and then we're just going to cancel out the 1 minus gamma, and then subtract 1 from the power. So evaluate this at ct plus 1 and ct. We can then get this then, now, as it was written generally, we can't really estimate that without saying something about the utility function. So we got to somehow, of course, make some restrictions on the kind of utility function this is, and we're going to say we know what the utility function is up to some parameter gamma. Once we know the relative risk aversion coefficient, then we've got the utility function. So again, that's another strong assumption, but if we assume this, then we're going to get ct plus 1 minus gamma rt plus 1 minus u dash, minus ct given zt equals naught for all zt. So now, well, if we've got data on consumption and interest rates, well, we can then measure this for any gamma and beta. So now we parameterize this as a function of beta and gamma. So these are the model parameters. Okay, so we've got a conditional moment restriction from our model where we've assumed, of course, all the conditions behind the Euler condition. So we've got intertemporal consumption and perfect foresight and all the assumptions that it makes. We've also assumed, and rational expectation and so on. We've also then assumed a constant relative risk aversion utility function, and that we've got some information from the information set, some ZT. Often it's going to be past values of consumption and interest rates. This then holds. The next bit then is to make a moment condition from this. Well, we can see then, we can write this again. We've got this conditional moment restriction, EB. Again, we can measure CT plus 1. We can measure the interest rate minus CT minus gamma given ZT equals naught. Again, this is for all values of ZT. So if the average is not, we can then multiply both sides by ZT. So I think they call this a conditioning theorem. Well, this is also not for all ZT. If it's not, if you multiply it by anything, it's also not. So multiply the right by ZT, it's still not. We can then take expectations on both sides and again use the law of iterate expectations. Again, the left hand side's not, right hand side's not. So when we multiply it by Z and take averages, it remains not. Well, by the law of iterate expectations, this is just equal to the expectation of beta CT plus 1 minus gamma times ZT. We've now got a moment condition, an unconditional moment restriction. So the whatever if all those macro assumptions hold, this rate of time preference and the relative risk aversion coefficient should satisfy this moment condition. And assuming that ZT is m by 1, we've then got from this m moment restrictions for 2 parameters. We're going to need m at least as big as 2. Technically here, so the solution says there's just the number of moments you're going to get is a dimension of Z, the number of elements in Z. Well, actually we can see there's more than that, because you could also use ZT squared or cubed, because going back to the above, this held, doesn't matter whether you multiply it by Z, all the elements squared or any function of ZT. So technically you can create an infinite number of instruments. You can take ZT, ZT squared, all the variables squared, cubed and so on, because this, when we went back to the above, so go back before we took expectations on both sides. Remember, we had this restriction here equals naught for any value of ZT. So we could multiply it by any function of ZT and it will still be naught, and then take that. That would mean then we can have any arbitrary number of instruments. And that's often sometimes used. So we'll come back to these ideas, but this here then we can see, but just taking the simple case, we can just take ZT as instruments and we can see all those macro assumptions led to that conditional moment restriction, and was able to find a set of unconditional moment restrictions which beta and gamma were assuming satisfied. So in this case, it's not as straightforward to see how many solutions there are to this. So broadly speaking, we're just going to have to assume that there's just a unique solution to this. There could be more than one solution, but again, it's hard to see because it's a nonlinear function of beta and gamma. But whatever's the case, we've got a moment restriction, and we're saying that these model parameters satisfy this. And again, if all the assumptions hold, then we'll pin down the true parameters. Whether or not we do, we still want to assume that this has just got one unique solution. If it's got multiple solutions, this will cause problems for estimation. But we're not going to talk about that now, but that's the idea. And that's the answer to question 2. And you can see now the kind of generality and the real usefulness of the method of moments and GMM, which you're going to come on to in more detail, I think, with Arena in the next lecture, is that you can create then, we can then solve the sample version of this. So you can create moments from this, and you can then go about using this population restriction to come up with estimates of beta and gamma. And this was one of the key ideas of the Hansen 1962 paper, and the GMM estimator is used all the time in econometrics. So we'll leave it there. Hopefully that was helpful. We got it down to just about an hour, so that's not too bad. So yeah, I can make some more clips if you're finding them useful. We can go over some of the other tutorial questions that we didn't get time for, and as we get nearer to the exam, we can do some revision sessions. And I guess the good thing is, it doesn't matter where everyone is, because we can do them online. So even if once the lectures are finished, we could still, if people are interested, or if you've got any suggestions, then we can do some more video clips. So we're going to go. So hopefully it was alright, and I'm assuming people were watching. So I shall see you on Monday for the final tutorial. So I shall see you later.